In this video, we are going to be looking at section 9.1, where we introduce the idea of limits, which will be an important idea as we develop our understanding of the main topic in the course, which is going to eventually be derivatives. But we're not there yet. So the way we define a limit is we start with a function, just a regular function, and it needs to be defined everywhere around a value c. C is just an arbitrary number, but it's not necessary that the function is actually defined at that value. So we define L to be the limit. It's the limit of the function as x approaches c if the y values of our function, so that would just be the function values, approach that number L whenever our x values of our function approach c, and that would have to be true from either direction. So you can think of the limit, which is L, as the y value that my function is approaching. So one way to think about this is it should look visually like the function is getting closer and closer to a single y value from both directions. Now, in the context of an example, this might be an open circle or it might be a closed circle. It doesn't matter when we are thinking about limits. And then whatever that y value is that we're getting close to is the limit L. Now, if it happens that we don't actually approach a single value as x approaches c, we would just say the limit does not exist. So this would happen if you approach two different values, or if you just don't approach any value, if your function values, if your y values go off towards infinity or down towards negative infinity. All right, let's go ahead and look at our very first examples. So for this first function f, I would like us to consider what is the limit of f, and I'm going to say that x is approaching, I could pick any number, but I'm going to pick the number that is indicated on the graph. So I'm going to say let x approach 2, and we want to say this is equal to something. Now, when you get competent with thinking about how limits work, it's very possible just to look at this graph and tell me immediately what the answer is. However, as you're trying to develop your thought processes for how do we think about this, it might be helpful to think of an illustration. So you can imagine that you are living on the graph, so that's me over here, and if I'm on the graph and I am approaching the x value of 2, right, x is 2 right here, but on the graph I would have to approach it this way, I might ask myself, what is the y value that I'm getting closer to? Okay, it looks like I'm approaching the y value of 3, but then you also have to consider what if somebody else is on the graph on the other side, and what if they are approaching that same x value of 2? The question is, are both of these people approaching the same point, or are they approaching different points? Is there a single y value that both individuals are getting closer and closer to? And in fact, there is. For this example, we see that both of our people are approaching 3. So we say the limit of the function as x approaches 2, you can think about that from either direction, would just be equal to 3 because that's the y value right here that we are getting close to. Then we jump to the next example. I want to ask the same question. What is the limit? This time our function is called g, so I'm going to say what is the limit of g of x as x approaches 2? And here we have a hole in the graph. So the function is not actually defined at that point. However, it doesn't need to be defined at the point for a limit to exist. So you think about if you were on the graph a little bit to the left of the x value that was indicated, so we're a little bit to the left of 2, if you start traveling towards the x value of 2, what is the y value that you're getting closer and closer to? We see that it's equal to -1, like that's what we're approaching. What if somebody else was on the other side of the graph, and they start approaching x from the right side? Are they also approaching the same value? We see that they are. So since both of these people are approaching the same y value as they get closer and closer to the x value of 2, we say that that y value of -1 is the limit of the g function as x approaches 2. So we can go over to our last graph and ask the same type of question. What is the limit? This time the function is called h, so I'll ask what is the limit of h of x as h approaches 2, and you see something a little bit different happen here. We have an open circle on the graph and we have a closed circle somewhere else. So we'll have to think about how we interpret those as we ask the question. But the question's the same. What is the limit of the function as we approach 2? So you think to yourself, if you were on the graph to the left of the value and you start approaching the x value that's indicated from either direction, so maybe you were to the left, maybe you were to the right, what is the y value that you are getting closer and closer to? Here, we're kind of ignoring the fact that there even was a point up here. It looks like we're getting closer and closer to this point, so I would say that y value we are approaching is equal to 1. So that's how we think about limits. We also want to just make sure that we remind ourselves about other notation that we are familiar with. So if I ask you on this final example, what is h of 2? This is a very different question than asking the limit of the function as we approach 2. H of 2 is asking where did we define the function. So you're looking at the x value of 2. There are two potential options. It's either the solid dot or it's this open dot. The open dot means we did not define the function there. The solid dot means we did define the function there. So when my x value is 2, we defined the function to be 4. So up here, I'll say that h of 2 is equal to 4. If we go over to the first example, if I ask you what is f of 2, you could scan the x value of 2. Did we ever leave a solid dot somewhere? Yes, we did. So we defined the function at 2 to be equal to 3. So we'll say f of 2 is equal to 3. Now, what we see happening over here is something that we will care about later, and we're actually going to define it with a mathematical term. Anytime the limit of the function is equal to the function, so both of these values are the same, we would say that at this value our function is continuous, and that'll be something we care about later. Let's look at g of 2. What we see here, as we're looking at this x value of 2, there is no place where anyone has bothered to define the function. All we see is an open circle. So the function has never been defined, and we will just say g of 2. You can either say is undefined, or you could say does not exist. If we want to get particular with our verbiage, it's better to say that g of 2 is undefined than to say it doesn't exist. The reason it doesn't exist is because nobody has bothered to define it. But both of these are true statements. It's just that the first line is the reason we say it doesn't exist. But for the purposes of this class, in a brief calculus class, I'm not going to get real nitpicky with how we are saying these, since the meanings are so similar. So the next thing that we want to define are one-sided limits. What we see here is we can define a limit from the right, or we can define a limit from the left. Looking at your notation here, when you define a limit from the right, what we do is we put a superscript above the number that we are approaching, and it's either going to be a plus if you are coming in from the right, or your superscript will be a minus sign if you are approaching from the left. Now, it's easy to confuse this with an exponent. These are not actually exponents. It's just a little bit of extra notation so that you don't have to write the phrase from the right or from the left every time you draw out a limit. Okay, so the way you read this, it's the limit of the function as x approaches a value c from the right, limit of the function as x approaches c from the left. So what we have written over on the right is like a little bit more mathematically broken down for like what we mean, but we can talk about it in the context of the examples that we just did. So this first person that I drew over on the left would be the left-sided limit. If you are approaching the point from the left, we would check to see like what was the y value we're approaching, and the first guy approached 3, so we would say the left-sided limit was 3. Then if the person on the right, which is that second person I drew, also approaches the same value, then we get to say the right-sided limit is 3. At that point, anytime your left-sided limit is equal to your right-sided limit, then we can say the limit exists, and in fact, whatever those two numbers are, you got 3 from the left, 3 from the right, that's what the limit is equal to. if you ever run into a situation, and we're going to see this soon, where the left-sided limit approaches one number, but the right-sided limit maybe approaches a different number, then the overall limit, just the limit, does not exist. So both the left and the right have to both exist and be equal to each other in order to say that the limit exists. All right, let's look at some more graphical examples of limits. So we have a graph here, and I want to ask about almost every x value. Let's start with the x value of 1. So what is the limit of the function as x approaches 1 from the left? So we see that the x value of 1 is here. If you approach from the left, if you like, I'm going to stop doing this at some point, but if you like, you can imagine a little person is on the graph and they're just approaching that x value. You would ask, what is this little guy, what is the y value that the person is approaching? So the y value that my function is approaching as the x values get closer and closer to 1 from the left would be 0 in this case. All right, similarly, if we are living to the right of the function and we are approaching this same x value of 1, it looks like we are approaching this same point here. So I would say the limit of the function as x approaches 1 from the right is also equal to 0. Now, because those two things are the same, we can say that the limit of the function is in fact equal to 0. However, if we are asked what is f of 1, f of 1 refers to how we defined the function at 1. The open circle means we did not define the function, so we scan, is there any solid dot anywhere where somebody has defined this function at 1, and there is not, so we'll just go ahead and say that this thing is undefined. Is undefined. I know that students like to abbreviate things, so if you want to use the D&E abbreviation, the meaning is similar enough that it's fine to do so. Let's think about the x value of 2. So what is the limit of the function as x approaches 2 from the left? Well, you scan the function. If you're approaching the x value of 2 from the left, the y value you are getting closer and closer to is this y value, so we scan over and we see that the y value would be 2. So we would say this equals 2. What about if we approach the x value of 2 from the right? So if you live over here, this time if you approach 2 coming in from the right, the function doesn't actually approach a single number. It just looks like it continues to go down farther and farther and farther. And the idea here is that we would be looking at a vertical asymptote if the function just continues to go down forever. So in this class, in a brief calculus class, we only define limits if they are equal to a finite number. There is no number we are approaching, so I'll say this limit does not exist. Well, when we get to the actual question of what is the limit as x approaches 2, this thing cannot exist because the left-sided limit and the right-sided limit are not the same number. So as soon as we see that the left and right are not the same, we can say the limit does not exist. We might also ask the question, what is f of 2? And if I ask that, I'm scanning the x value of 2. Is there a place where we have put a solid dot to define what the function is? Not so on the left, and on the right, it just goes down forever. It never actually gets there. So here, we would also say this does not exist. Does not exist. All right, 2 more questions. Let's think about 3. What is the limit of the function as x approaches 3 from the left? So if you're approaching 3 from the left, the y value you're getting closer and closer to here looks to me like it would be 1. If we approach from the right, it also looks like the y value would be equal to 1. Because those are the same, we can say the limit is equal to 1. And then when we ask what is f of 3, you scan and you see, hey, we did leave a solid dot here, so f of 3 is also equal to 1. When you see this type of behavior where all of these are the same number, that one implication of that is that the function is continuous at that value. Now, we aren't talking about continuity per se in this section, but we will talk about it in other sections. What about 5? If you approach 5 from the left, we should be approaching a y value of 3. If you approach from the right, you also approach that same y value of 3, so then the limit of the function is defined to be 3. However, f of 5 is not 3, because when we look at this, even though we're approaching the y value of 3, we actually define the function to be 4 at that value. So f of 5 would be equal to 4. Now, just to be clear about the way that we use this notation, if I ask what is the limit of this function as x approaches 6, even though there's not a point listed here, the assumption is that it goes through whatever the point would look like. So if I'm approaching 6, it looks like I'm getting closer and closer to this y value, so we could say that that is equal to 2. And then similarly, if I ask what is f of 6, even though you don't see a solid dot listed anywhere, the line is solid, so the implication is that it's also defined to be 2. So this is equal to 2, and together that would also mean that we are continuous here. The next thing we want to talk about when we talk about limits is we want to try to understand them analytically. So we begin by discussing some properties of limits. The first property would say that the limit of a constant as x approaches any arbitrary value is always going to be equal to that constant. Now, there's a nice little picture that goes along with this. I'm not going to draw a picture for every one of these properties, but I wanted to do it for this first one at least. To make this graph feel a little bit more concrete, I want to just suppose that we know what k is equal to. You can pick any number you want. I'm going to pick the number 20, but there's nothing special about that number. The next thing we would do is we would try to graph the line y is equal to 20, which would be the same thing as graphing the line f of x is equal to 20. So we find wherever that value 20 is, and if you recall, when we graph a line y equals 20, or just a constant function, what we have is we have a horizontal graph. The next thing we would need to do is we would need to decide on some x value c. It doesn't matter what c is. You can imagine like maybe c is 15, but c could be any number. And the question is, what is the limit of 20 as x approaches 15? So if you were on this graph and you start approaching 15, what is the y value that we're getting closer and closer to if you come in from the right or if you come in from the left? I hope that this graph illustrates, well, of course, the y value is just 20 because that's what we were on the whole time. So that's the meaning of this property. If k is a constant, it doesn't matter what x value we're approaching, the limit of the constant is always going to be equal to itself. All right, the limit of x as x approaches c is equal to c. Now, for this next property, we need to think about what is the limit of f and what is the limit of g as x approaches c. And that has been stated up in this top part of the screen. So what we know is we know that the limit of f as we approach c is going to be L, and the limit of g as we approach c is going to be m. So L goes with f, m goes with g. The property says if you are adding or subtracting these two functions together, it is fine to just think about adding or subtracting their limits. So if this had been an addition problem, then we just say it's L plus m, but if it had been a subtraction problem, then we say it's L minus m. In a similar manner, the limit of the product of two functions would just be equal to the product of the two limits individually. If we're dividing, we can think about it as L divided by m, although in this case, we now have to just specify that we never meant to divide by 0, so we have to indicate that this limit of our denominator wasn't actually equal to 0. If you were taking any kind of an exponent, or in this case it's being shown as an nth root, the property also holds, so you could think about this as just being the nth root of L. Let me say that again. The limit of the nth root of a function is actually equal to the nth root of the limit of the function. Now, in an actual example, n is going to be equal to just some fixed number. So if n is 2, you're thinking about the square root of this number. If n was 3, you'd be thinking about the cubed root of the number. Now, the reason we present all 6 of these properties of limits is that they would be needed to state the limit of a polynomial function. Here in the middle, we're going to define a polynomial function. This is a very mathematical definition, but it's not going to be super useful for us. Like, we're not going to actually work with that. The limit of a polynomial function, and this all comes from what we see up here, is the limit of f as x approaches c is always going to be equal to f of c. One implication of this that we will see later is that this property is going to mean that polynomials are all continuous. When we think about rational functions have a numerator and a denominator. So if I ask what is the limit of that h of x function as x approaches c, this is going to be equal to h of c, provided, so I'm going to say if, the limit of our denominator was not actually equal to 0. So up above, we have called the limit of g of x m, so I'm just going to say if m is not actually equal to 0. Okay, let's look at our first introductory examples. So for this first one, what we have is we are being asked what is the limit of this function x cubed minus 2x as x approaches negative 1. The property up here says if you are ever trying to figure out the limit of a polynomial function as x approaches a number, you are allowed to just plug the number in. We oftentimes are going to call this property direct substitution. So using direct substitution, what I'm going to have is I'm going to have that this is equal to negative 1 cubed minus 2 times negative 1, and we find that this is equal to negative 1 plus 2, which is just 1. So the limit of the function as we approach to negative 1 is actually equal to 1. In these examples, if you're looking at a polynomial or a rational function, you always want to start with direct substitution because the two properties together say you are always allowed to just plug in the number. And the only time that's ever going to be a concern is if we somehow get a denominator equal to 0. So in this next example, we aren't going to think too hard about it ahead of time. I'm just going to begin by trying direct substitution. This would be 4 squared minus 4 times 4 divided by 4 minus 2. What we get is 16 minus 16 equals over 4 minus 2 is equal to 0 over 2. Now I see 0, but I shouldn't be concerned about that because it's up in the numerator. It's fine if your numerator has a limit that gives us 0. It's not fine if the limit of our denominator was 0. So here we end up saying this is equal to just 0. The next natural question to ask would be, well, what would happen if we had a 0 in the denominator? Are we able to actually do something, or are we stuck? So we're going to have two different cases, and in both cases, the limit of our denominator is 0, the limit of the denominator is 0. What we're going to differentiate then is the limit of the numerator also 0, or is the limit of the numerator not 0? So I'm just going to write this to the side. The first case would be if you try direct substitution on a rational function and you get 0 over 0, this is indeterminate. It doesn't mean anything in and of itself. The limit may not actually exist, or the limit may exist, we just have a little bit more work to do. So what we're going to try is we're going to try to factor x minus c from our numerator and from our denominator. Once we have done that, you'll be able to reduce the fraction. Then you're going to try to find the limit again. So it's basically like restarting the problem. At that point, you try direct substitution again on the new function. Let's go ahead and try that in this example. So we want to determine what is the limit of the given function as x approaches 2. First thing we do is we try direct substitution. 2 squared minus 4 over 2 minus 2 is equal to 0 over 0. So we see we are in fact in this first case, it is the indeterminate case. You don't need to write the word indeterminate down, but you would be welcome to. So we have to stop, and what we do is we basically are going to factor and restart the problem. So I'm going to rewrite the limit notation. I'm still trying to figure out the limit of this function as x approaches 2. I just need to simplify the function. Now the denominator cannot be factored, and we would check the numerator. Could you factor the numerator in any way? We see that in this example it factors as a difference of squares, so we get x plus 2 and x minus 2. Okay, we reduce. X minus 2 divided by x minus 2 is just equal to 1. If you want, you can even leave the 1 there. And now that we have reduced, we try direct substitution again on this modified function. So what is the limit of x plus 2 over 1 as x approaches 2? This would be equal to, we just plug it in, 2 plus 2 over 1, which was just 2 plus 2. So what we get is we get 4. Now, there was no way to know that our answer would be 4 ahead of time. If you see 0 over 0, you could literally get any number over here. We could design the problem in a way that we could generate any number as our answer. So from here, you just always try factoring and then see if you actually get a solution. Or you may, after trying this, realize there is no solution, depending on the type of problem that you run into. All right, let's go back up and look at the second case. In the second case, you still have 0 as the limit of your denominator, but you have some non-zero number in your numerator, or as the limit of your numerator. So just something that's not 0. If this happens, then the limit of that rational function does not exist. So it's not a finite number, we're just going to say it does not exist. What is going on behind the scenes, and might be useful to know, is that anytime you run into this behavior on a limit, x equals c is actually going to be a vertical asymptote of the function. So let's go ahead and try that second example that we see down below. What we have is we have the limit of this rational function as x approaches 1. We're going to plug in 1, so you get 1 squared plus 3 times 1 plus 2. And that's over 1 minus 1. So in our numerator, that will simplify to be 6. In our denominator, this simplifies to be 0. You see 6 over 0, and what you have to remember is you remember we are in the second case, which means that the limit does not exist. Any non-zero number over 0, we are just going to say limit does not exist, and we're done. So in some ways, this second case is a little bit easier maybe than the other one because it didn't require factoring. However, if you feel comfortable with factoring, you might feel like that first one's easier because there's no extra thing to remember and associate here. Now, the last thing that we're going to cover in these notes is we're going to talk about piecewise defined functions. If you are asked to find the limit of a piecewise defined function, probably we are going to focus on this number where the definition of the function changes. So in this case, we are asked to find f of 2, then the limit of the function as we approach 2 from the left, the limit of the function as we approach 2 from the right, and that should be enough information to determine what the limit of the function is. Before we actually begin and try to work with this at all, it might be helpful to remind you about what piecewise defined functions look like. Now, what I'm going to draw here is not a graph of this example, but just a generic graph of how you might think about piecewise defined functions. There's some value c that we are going to split the function around. So for the purposes of just argument's sake, let's pick on the number 10. I know that 10 doesn't show up anywhere. 2 is the number that shows up here, but I just want to make it clear that this graph I'm drawing is not actually a graph of this function. So if you split your function around 10, there's kind of two possible graphs that you might end up with. What might happen is you might have a function that is discontinuous. So a function that looks like this, where the left side is not equal to the right side, they just end up with two different y values. Or you might end up with a function that is continuous, so you have the left side and the right side happen to line up. If we are in the first situation, your left-sided limit is one number, your right-sided limit is another number, and then we would say the limit doesn't exist because we are not approaching the same y value from both sides. If we're in the second situation, the left-sided limit is equal to one number, the right-sided limit approaches that same y value, then we would say the limit exists because the left and the right are actually the same. So that's how we think about this problem. We think about what happens on the left, what happens on the right. If they're the same, then that's what the limit is equal to. But if these two things are not the same, then this thing, the limit, does not exist. Let's begin there then. So what is the limit of the function as x approaches 2 from the left? Now, because we are approaching from the left, we don't actually need to consider the entire function. We just need to consider the left side of the function. When x is less than 2, that is left of 2, the function is defined to be this. So I'm going to rewrite this notation using the left side of the function. All right, at this point, we just get to plug 2 into the function. Like this is a type of problem we've seen before. You kind of ignore the fact that we're approaching from the left. If x is approaching 2, we try direct substitution by plugging 2 into the function. So 2 cubed minus 4 over 2 minus 3. What we get is 8 minus 4 over 2 minus 3. So that's 4 over negative 1, gives us negative 4 by the end. Next, let's consider what is the limit of our function as x approaches 2, this time from the right. So if you're approaching from the right, x is greater than 2 means our x values are to the right of 2. So we are only considering the right part of the function. So I'm going to rewrite this notation using the right part of the function. We have limit of 3 minus x squared over x, and this limit was as x approaches 2 from the right. So we're plugging 2 in for x using direct substitution. Direct substitution, I see I forgot to write that earlier. Let me write that in, direct substitution. So using direct substitution, we get 3 minus 2 squared over 2, which gives us 3 minus 4 over 2, which is negative 1 over 2. Now that we have figured out the left limit and the right limit, we can compare these two and see, are they actually equal to each other or are they different? We notice, of course, that these two things are not the same. So what that allows us to say is that the limit of our function as x approaches 2 does not exist. The only way this could exist is if these two numbers had been the same. So if they had both been negative 4, we would say the limit is equal to negative 4. But if they had both been negative 1/2, we would say the limit is negative 1/2. The only thing we have not answered yet is the first part of the question. So let's go back and let's answer what is f of 2. I saved this for the end because this is maybe what you are most familiar with doing, and I wanted to first of all focus on how we think about limits. So if you are just asked what is f of 2 without any kind of limit notation, what your task is you need to determine which definition of this function allows x to equal 2. So you're looking for this equal sign, x is allowed to equal 2 in the top, so we're going to plug 2 into the top part of this equation. When we do that, we get 2 cubed minus 4 over 2 minus 3. This is equal to 8 minus 4 over 2 minus 3, which is 4 over negative 1, a number we've seen before, but we see that this is equal to negative 4 by the end. And that concludes this section of notes.